Good morning, good evening, good afternoon, everybody. Welcome to the January edition of the IREE community meeting.
I think we're waiting for Jack, but I think we can get started. Uh, so for people who don't know, I'm Mahesh. I work at the ED team in Google. And today I'm going to talk about some of the work that we've been doing within our team with contributions from folks at Intel related to data tiling in ED. So very basic, what is data tiling? As most people would probably know here, it's a way to get your operands into a layout so that you can map a basic unit of work easily to vector instructions without having to do complicated padding, peeling or masking or things like that. So to take an example, if you're doing a quantized matmul of I8 to get an I32, there are instructions on ARM64 devices that can allow you to do left hand side of 2x8, right hand side of 8x2 to get the final output of 2x2. Benma went over this a little bit in his talk previously in this forum. And then you could pack many of these instructions into one unit of work. So you could pack a few instructions as for the ARM devices to get an 8x8 left hand side, 8x8 right hand side, and that becomes your unit of work. To make sure that for all problem sizes you can map your computation into this unit, you would need to do some sort of padding so that you get your problem size to be a multiple of this unit. So that would be enough with padding. But what data layout transformations give you on top of it is it makes sure that you keep your data access pattern contiguous for the operands, even when you're executing across the different units of work. So that puts you in a better position in the space in terms of cache utilization because all the accesses are contiguous. It removes a lot of complexity from the code that you would have to generate to handle multi-level caching, all of these things. You might still need that to get like a last bit of performance, but by default, you're hopefully in a better state.
I think we've got an audio issue, so
Oh.
can we interrupt and pause for
Restart
a
again?
second?
Sure.
We might not be restarting, but I'm not sure if
Yeah,
others can hear us, and I don't think we're hearing them.
I had the same issue in the morning.
yeah.
Okay, Jacques says they can hear us.
Okay.
Yes.
But we cannot hear them.
I think we can hear them.
Let's maybe try exiting here and then re-entering. Will that break the recording?
No,
I know.
someone else did the record. Just that all of this will be recorded.
We can see people. Your mic. Can you hear us?
We can hear you. Can you hear us?
Okay, we can
Okay, it's
All right,
fixed. Turn it off and on again.
Cool. So I don't know if there are any questions before. If there weren't, I'll go ahead. But if there are questions, please feel free to raise your hand and we can take it as we go along. Yes, there was. Ben had it. So at a very basic level, what data tiling for GEMIC for linear matmul boils down to this picture. If you have one kernel that is doing a matmul, with data tiling you would have 4 different kernels. Again, what each of those 4 are, or over the course of this discussion, you would pack the left hand side into a particular layout, right hand side into a particular layout, then do the matmul computation. In this example, using the MMT4D op, which creates the output also in a pack layout, and then you have the last dispatch that gives you back the linearized output of the manual computation. So if you take just a matmul and you try to do data tiling with it, that's what you would end up with. So these are 4 different dispatches which loosely map to kernels on CUDA basic execution unit in ED terminology. Going a little bit more into the details of what the pack and unpack operations are, it takes, just looking at the operation itself, it takes a source, which is a linearized tensor. It takes a list of inner DIM's position. Naming is hard, so the name is a little bit convoluted, but what it is giving you a list of dimensions of the linearized source that you want to tile. So in this example, the value is 0 and 1, which is saying that both the 0 dimension and the first dimension of the source needs to be data tiled. The next is the tile sizes, which is architecture dependent, and they correspond to the tile size you would use for each of the dimensions in the order that was specified in the inner dims position. I'm not listed explicitly here, but there's also an outer dims permutation that allows you to permute the the dimensions of the packed tensor on the outside. So not the inner tiles dimensions that you get, but the outer dimensions that are going over the tiles. So this is an explicit conversion of rank. So now if in this example you start with a 2D tensor, you end up with a 4D tensor. So to make sure that your tensor is well formed, you will need to do some padding in case the tile sizes don't divide this problem, the size of the original source tensor. So the pack operation in general has padding semantics. The reverse operation, which is the unpack, looks very similar, and just like the reverse of the pack, the unpack has slice semantics. So you get back the slice of the output that you would need to get back the original result. So in specific case of the ARM ARM path that we are currently looking at, this would be the packing you would use for the left hand side, and that would be the packing you would use for the right hand side. Here the inner tile size is 8 and 4 for both the left hand side and right hand side, but the thing that differs is on the right hand side you have the outer dims permutation being 1 0, which says that you're doing a transpose on the outer dimensions, and the inner dims position, instead of being specified 0 1, is specified as 1 0, which means that your inner tile is also transposed. So this gets your right hand side matrix into a layout so that as you access the right hand side, everything is contiguous, and the same happens for the left hand side. Going to the compute operations, you can't use a linearized mathematical directly because that works on 2D tensors. You would need to use a different operation that can do the same computation, but now on a higher dimensional tensor. So there is an operation which is the MD4D operation that was added when we started looking into this path a long time ago. So we can still use that operation. It just represents a tiled matrix multiplier execution. Recently, Nicola landed a few patches that can take any linear op and convert it into a higher dimensional linear generic op, which does the same computation but in a tiled fashion. The advantage here is that by construction, the unit of work, which is the inner tiles of this computation, are vectorizable. That's the reason why the packing was done in the first place, and you get better memory access pattern. So the code generation for this to get reasonable performance should be fairly straightforward. And this has been before we started doing the data tiling work in this context, we already had a path to target MD4D operations. It just had a long layering. So within that, we'd already seen that it was able to get good performance, matches the performance that was achieved through RUI. And in reality, all the approach that is being taken here is derived from what RUI used to use for matrix multiply. For context, RUI is a library that was developed by Benoit for matrix multiply, high performance matrix multiply kernels on ARM architectures. So now with the data tiling, you get your core compute operations are in fairly good shape, but there's no free lunch. The thing that needs to be addressed here is the amortizing the costs of the packing and the unpacking. In general, there are two ways of doing it. The first, more local approach is to try to fuse the packing operations with the producer, and conversely, the unpacking with the consumer. The way we try to get this working is both these operations implement a tiling interface. It's an interface for tiling that's been developed upstream, and the properties of that is once an operation implements that interface, fusion with producers comes out of the box. So it should be easy. by default handles fusion of packing with its producers. Fusion with consumers is a little bit more involved, but we have an implementation of it, but it's not as straightforward as fusion with producer. The other approach that you could use to amortize the cost of packing is by propagation. So you can look at the source of the packing operation and then do a data layer transformation on the operands of the operation producing the source. So in some sense, you're moving the pack operation above the producer so that you're now packing the operands of the producer and you get the result in the layout that you want. In general, that's a harder problem. It's not always clear that you can always propagate the pack across any producer. And it's also an issue of profitability. The layout that you want the output in might not be something that you can use in a way. It might not match the layout that you would want for the producer operation. Sorry, I can't see what Ben was written in the chat, so I'll let people go.
Also in practical ML applications, many mapmul operands are compile time constants, so packing of those can be done by constant folding. Time to play with still has passed from December.
That's right. Actually, that's one of the things that we need to resolve to land this part fully. More broadly, in a whole program context, it's a harder problem to find ideal placement for these packing operations because you might have different operations that need different packing. So it becomes a constraint solving problem, which gets harder with arbitrary control flow. So the easiest thing to do first is to try to just do the fuse the packing with its producers and try to amortize the cost that way. If that is not sufficient, then we can try more complicated solutions. Okay, so this was just about packing and getting the code generation. What you need to do in the code generation side of things to get the code that you want. The next question was, how do we support this in IREE? Before I go into details, maybe just a bit of background on like overall flow of IREE compilation as required for this discussion. There's a flow dialect is where you identify atomic units of work. So you take your input program and you partition it into units of work that map to a dispatch region. Loosely a kernel on CUDA. Not loosely, it exactly maps to one kernel on if you're writing a CUDA, if you're targeting CUDA. And this part is architecture agnostic, so we don't know specifically what architecture you're targeting. Then the stream dialect is responsible for scheduling these dispatches, and the HAL dialect is where you have the information about the architecture that you're generating the code for. With it, for the data tiling approach, you would have to move the packing and the unpacking operation into their own dispatches so that you can pre-process the data into the layout you want. And because the pack and unpack need the inner tile sizes explicitly, and that's not something that you have available at Flow, doing this in architecture agnostic way using the pack and unpack was not feasible. Yes, Nicola.
Yeah, I have a question on that last point because something seems a bit off to me. So let's see. Where do allocations happen? Whatever is given to the HAL level, like somewhere these, the graph level bufferization at some point happens. Where does that happen?
That's in the stream dialect.
I see. And the stream dialect doesn't know anything about the backend, right?
Correct.
Okay. So I guess I'm seeing, or it feels like something that feels a bit fishy to me, because if you're doing allocations in a target independent way, it means there must be some size that is good for everything. Is that true or not?
There needs to be a size that is good for everything you're targeting. And so we're architecture agnostic, but we're not necessarily informationless. The goal here is to not necessarily be able to create a program that will run on any arbitrary thing. But if the user says, I want to run on these 3 different shader model architectures or these 4 different ARM CPUs, that we would pick between those, as opposed to saying this one specific hardware instantiation. So we're architecture agnostic, and we try to be general there so that we can do things like that, as opposed to requiring entire copies of the program, even if you're targeting, little and big cores on the same physical device.
Right. Okay. And so does that mean that we could technically use pack unpack ops with those common tile sizes at that level? Is that accurate?
The padding of the allocation is really the only thing that matters at this level, not the actual dimensionality of tiles. Because the only thing we care about on the outside is that we can call, ku mem alloc with the right byte size. We never actually touch the contents. All the contents and how you actually process the data is done in the dispatches that are hardware specific. And so one of the assertions at this level, if you're targeting multiple devices, is you really just need to be able to allocate the right amount of memory. And that padding that we choose to do on that memory allocation is something that can be queried all the way to runtime. We just don't.
But today, and we can. I had something later on that was specifically addressed to us this point. So
Okay.
Another
So I guess I'll
question.
wait.
Oh, sorry. No, go ahead and finish, Nicola.
I was
said he'd
saying,
wait.
great. I guess I'll wait for the next.
Okay. Someone else has a question on the chat. I just wanted, because I know that you can't see those.
yeah, I can see that.
Where does the progressive lowering occur, like various generic optimizations on SCF standard affine? Are they even applied to stream dialect? This is Samarine Joshi.
So graph level transformations, I shouldn't use graph. Program level transformations happen at the flow level. And then when you have what you want to target as a single kernel, lowering that into the final scalar code happens within the HAL dialect in the backend. So that's all the backends are basically nested within the HAL dialect.
Yeah, conceptually at the flow level, you're basically just saying, I want to do, these 2 units of work, and here is the buffer that needs to exist between those. The stream dialect just makes sure those buffers get allocated, and then the HAL dialect is the thing with the code gen on there that actually acts on those buffers. And so that if you were to draw this as a pyramid of kind of like deployment configurations that fan out, the flow dialect, we try to keep that as small as possible. Because any additional configuration we need to support there, combinatorially explodes the whole problem. Whereas once you're at the HAL dialect, if you want to multi-target and multi-version, and specialize for different architectures, you can do that much more effectively. You don't, in a lot of cases with this tiling stuff, need to specialize, basic element-wise operations and things like that for different architectures, but you might decide for your comms and your mapmols to do that. And this gives each one of those target backends the ability to kind of make those decisions as it needs to, based on what it's actually generating.
Ojo?
Yeah, so just looking at the last point there, if the pack and unpacks, if they're not added to the flow or at the flow level, where are they added? And how can you form dispatch regions around them if that's
That is in the next slide.
Okay. Then I'll wait to the next slide.
Okay, so at the flow level, what you only need is that you need to know that a particular tensor is going to be data tiled. You don't need to know the specific layout that you're going to use. And you also potentially need a way to disambiguate between different layouts you want to use. Like the left-hand side of a matrix multiply has a particular layout, right-hand side has a different layout. You don't know the specifics of that layout, but you just need to know that they're different. So restating the problem, you need an abstract representation of data layout at the flow level, and that's enough for everything you need to do at that level. So we decided to hook into the tensor encoding mechanism that exists and is being used by the sparse dialect work being done upstream. So for operations, for tensor values that we know we want to change the layout, we have set and set encoding operations that take a tensor value and just add an encoding to it. It is a representation to say that IREE by default treats tensors as row major linearized. The encoding tells you that the actual tensor layout that you're using is different from that default. So the way data tiling gets injected into the program is there's a pass today that goes and looks at each linear map mode and adds the set and unset encoding around its operands to signify that the operands are being data typed.
And one nice thing about this is the same thing we can use for a bunch of other techniques. So sparsity is the thing that kind of originated the tensor encodings that we're using here, because block sparsity is a type of data tiling encoding. And this kind of uses the same thing. Other things we can end up doing with that are compression and then optimal image formats when we're targeting GPUs that have support for that. Whether you are using a DXT compressed image or something is an encoding on a tensor that you would be able to encode in the same way.
Right. So going back to the sparse dialect stuff that Ben was talking about, the tensor encoding that they use in sparse dialect is pretty rich based on literature. Today we wanted to be as less opinionated as possible so that we don't over design it. So it's just an enum attribute that is a way to distinguish between the different layers that we are looking at. As time progresses, maybe we understand better what these encodings should be and make it richer. But for now, we're just starting with the most simple thing that you could do. The good thing is that the encoding just propagates to the stream dialect. It's basically a no-op for the stream dialect. And when you get into the HAL dialect, you can treat each of these encoding enums and convert them into the combination of the outer dims permutation, the inner dims position, and the inner tile sizes for each of the encoding. Based on the architecture that you're generating code for, because at the high level, you have all the details that you need to make this decision. Thing that I didn't mention earlier, the inner tile size can also be dynamic. This is actually not part of our initial exploration, but we needed it to land some of the pieces that we want to move under this framework. So the inner tile size can be completely dynamic and be runtime configurable. And this is being used today. This works well for compute operations as well. So when you form the dispatch, you would have a linear.matmer, which with the operands having the encoding on them. I just changed the actual encoding to be more fit into the slide. And then you can convert that into the lineage MD4D operation and use the stuff that Nicholas landed upstream to convert any lineage op into the corresponding lineage generic. And from there, everything is explicit. You know, the explicit tensor dimensions, explicit layout, and then your code generation just has all the information that it needs.
And it sounds like this is, with Nicholas's changes, which I've not reviewed, this could potentially fold in and apply to other algos.
Pretty much, yeah. And just what you do for Magma, you do it for any other. We just use the MD4D because it existed. Yes.
Sorry, I was going to mention that there are limitations. It's not like everything just magically works out of the box. Some of the limitations include basically it has to be some sort of permutation. Otherwise, you need modulo and div operations. So if you want to, let's say, data tile the image of a convolution, for instance, since it's accessed by a kernel, you will need actually an operation that has div and mod, and lineage does not have that. So on convolution, you can only tile or data tile, sorry, the batch, channel, filter dimensions, but not the other ones, at least not within, it's not closed under lineage, let's put it this way. But I've been thinking about other type of structured ops that could also work with that, but this would require extensions. Anyway, so just a word of caution is like it works for permutations. That's about it.
And I think that covers a vast subset of things that we need, like for convolutions. I think that is what would be important too. Okay, so let's a little bit more on the pros and cons of using the encoding mechanism. One is that the upside encoding allows you to not leak architecture details of the compilation stack. There are ways we can try to structure the problem to get around that, and we can discuss that later. The other benefit that might not be as obvious is that the rank and shape of the tensors don't change very early on in the program. So if you try to do it at the flow level, it means that you have to change the computation into something else because your explicit tensor layout has changed. So if you had a lineage.matmut in your flow in your program, at the very beginning, you would have to convert it into something that is not that. And having that semantic information is useful. It's better to keep that later on in the pipeline to actually till you do the code generation. So that's a big plus. And like Ben mentioned, it's similar to how sparse tensors are being handled. Pretty much the encoding is used for the same reason that you can keep a lineage.mat mode operating on tensors or sparse type, but your core computation hasn't changed. And it's only when you start generating the code for it where where the layout becomes important. What are the downsides of it? There are potentially missed fusion and optimization opportunities. It could be that the two encodings that you use are the same in a particular backend, and you don't have the information to fold it away at the flow level. It could be that an encoding turns out to be a no-op, and in that case, you don't know that at the flow level, and you've already created those dispatches, which end up being a copy. So that's that's some inefficiencies that we still need to work out how to address.
But that would only be the case if it was a dispatch that, like a pack that could not be put with its producer. If it was put with its producer.
Yeah, if you fuse the pack with the producer, then if it's a no-op, then it's a no-op in the producer. So then it just, you basically don't see it. But yeah, you're right. If your pack is in by a dispatch by itself because it couldn't fuse with anything, then you might have some inefficiency. So that's good. Propagation is also harder because you're working on abstract types. So it makes it harder to reason about how you want to propagate it. We haven't looked at propagation, so we're not really thought a little deeply about whether it actually works on it with encoding or not. There might be a solution that works even on encoding types. Just haven't considered it in a deep fashion. So that's an overview of the data layout transformation work that's in IREE. The current state of it is we started with the ARM path targeting MT4D as the first mover on this because there was a lot of work done previously under the MT4D umbrella for targeting microkernels, generating efficient code, inline assembly through the MT4D op, and this allowed us to get all of those working without, as well as address the architecture detail leak that was happening at the flow level with the previous path. So all of those things have now been moved under the data layout change purview. So it's all enabled under the same work. So far, we only looked at within IREE, we only looked at the linear.mat mode operations, and we made a specific choice to say that we are going to have both the operands and the result be in a tile layout. That makes it simpler to write the microkernels and also connects to MT4D. So that was the decision made there. The downside is that it does prevent fusion of consumer operations with the linear.mat mode because now you have an unpack operation in the middle. So you can fuse with the unpack, and there's really no point fusing past that. At least for now, we might reconsider that later. The upside though is one of the motivations we wanted to go down try this approach was right now the way we generate code for our models, we effectively end up generating a unique dispatch for every mat mode code that we have in our computation. So we have a huge binary size. Eventually we want to get to a place where in the limit we have a single kernel for all the mat modes that you have in the model, so that can really reduce your binary size. That has real effects on instruction cache usage. And in that scenario, fusing a mat mode with its consumer might not be something that you want to do. So it depends on trade-offs between binary size and performance, and that's a study that needs to happen. So for now, we felt it was a reasonable path to go down. So that's what's implemented today. It's very easy to change it to not have the output being in a tiled fashion, in which case it would get you back to allowing fusing your mammals with a consumer, which is like an element-wise operation, like we do today.
Yeah, and we should unpack should be really easy to move element-wise across when we do this.
Yeah, those are again propagation, and haven't really looked into that part of things. So, given that we took a particular choice, what are the other choices we could have taken here? Like I said, the reason we went down this path was primarily to be able to target the same MT4D paths that exist today. So I'm repeating myself here, where you could not generate the output in a tile layout for your after data tiling. So when you set the encoding, you don't set an encoding for the result. That will put you back on the path where you could fuse your manual computation with the consumer, and that should work out of the box by just changing the encodings that you use. It's also possible if you know that particular hardware that you're targeting and you're interested in only that particular hardware, you could use the pack and unpack operations and do it as a pre-processing step before what IREE does as compilation today. So if you know exactly what you're targeting, that's a thing that you could do. And the pack and unpack are supported end-to-end like any other operation because it follows the same path that IREE uses for all other operations today. So that could be done as a pre-processing step if you're interested in a particular target. It's a matter of trade-off of what you want to focus on. So if you're trying to achieve peak performance on a particular use case, that's an option. We haven't really built that option out, but that's one thing that we could do. So far, we've been looking at generalized performance out of the box on a wide range of hardware. So you might not be getting peak on any particular hardware, but you're getting reasonable performance out of the box. That's the goal. So this is the path that we've taken so far. And the understanding was that the data layout that we're using for the ARM path is a reasonable data layout on a wide range of hardware, including x86. So we need to actually work out the profiles and make sure that that's the case and see the trade-offs. That's part of the work that we're going to do next. I haven't included any performance data in this talk because a lot of the performance data we have basically comes back to the MD4D performance. So the next step in this work is to really look deep into profiles to see how much we're amortizing the cost of the pack operations. If we're not doing that, what's the impact on producers when you fuse the pack with the producers and then try to mitigate those things. That's the next steps. As part of this work, the microkernels that were written by Benoit that were used on the VMVX backend, we'd also like to start using them on this LVM CPU backend. Benoit filed an issue that describes why using microkernels on x86 might be important as well for getting good performance on x86. So we have some initial ideas how we can do this, but we haven't started work on that part yet. There are a few folks looking at data tiling on the CUDA and SPIRV backends. That's yet to kick off though. And then part of this work was done in collaboration with Intel. I think some of them are on this call. Lorenzo primarily contributed a lot of the code for the pack and unpack and upstreaming it. They've looked at using these operations to get good performance on convolution-based models, and they've demonstrated that within the TPP effort that they're driving. So we probably try to use a similar approach within IREE under this umbrella. Nicola is doing some initial work in prototyping those things, and as we get more information, we'll fold that into the IREE compilation flow by default to improve our convolution performance. So those are the next steps. And I think that's the end. I don't have anything.
Awesome.
Any questions from people on the call?
Goenka?
Could you please go back to, the, let's see. Yeah, exactly this one. How about, let's see. Yeah, so you mentioned, the pre-processing step and then architecture information. How about using the fact that we can data tile by parameters, basically by symbolic variables, and then plug them later? What do you think about that?
That was one of the options, but I think it would be really hard to manage where those symbols come from and where they get materialized and make sure that they get in a consistent manner across all the programs. That's an option too. I think we could keep that as a runtime constant, which just gives you the value. Kind of what Ben was hinting for the padding as well.
Yeah, that's effectively what we would have to do, because where we perform partitioning and actual placement of dispatches onto devices and deciding which dispatches are getting compiled for which architectures is in the stream dialect. And so if we were to have free floating ops before that point, it becomes much harder to place them because, you know, those might get hoisted out into globals done at initialization time or whatever, but now you're kind of very far from where you actually need to be scheduling these things. And so having something that is a unit that we can kind of move around together with the ops that are actually consuming it just makes that a lot easier. We can outline things, we can, you know, inline functions, we can kind of do all that stuff very freely.
Part answer to that, Nicole, I don't know if you agree with it or not. It's easier to model things in types, gives you more guarantee than modeling in operations. It seems like a similar trade-off here.
I mean, it's always the same trade-off, right? Is SSA values versus attributes. So, I mean, one of the downsides that you didn't mention is that with the encoding stuff, either we need to find a way to encode all the data tilings we might want in attributes, or we're going to start having, you know, this enum atter is going to grow and it's going to be implementation specific, one case at a time. Each time you want to add a new op, each time you want to support a new op. So
the intent is that we use attribute interfaces there. And this is, again, like the concept of this being effectively like a library call for, you know, turn this data into some other form of data, shuffle the data, permute the data, something like that. The thing that actually decides what the implementation of that library call is the attribute. And today it's done as an enum, and then it selects and just decides, you know, do the library call for a left-hand side of a matmul operation. But that can be entirely pluggable. And so it then becomes a question of, and this might be what you're getting at, of, is it possible to build a library call for the kind of transformation you want to do, or are you generating something that inherently is not library callable? And that then may change things, but if you can conceptually think of this, like if you were writing a library and there was some pack function you wanted to call, what would be the name of that function? That's really all that this is encoding.
I think you two are saying two orthogonal things, though. You know, you're saying that, and Nicholas is saying, how do you, what if the function took a parameterized type? You know, what if it wasn't just an enum, but it was symbolic in some way?
What would that be?
I don't know. That was
Yeah.
the question. That was the question.
Yeah, it should, you know, if we're able to generate code that uses this stuff effectively, we do ostensibly need to be able to derive it. And if it's based on the problem being performed, that gets much harder because it's kind of like until we're actually executing the code, we wouldn't know which path to do. So it's a good question if we can find examples of cases where.
I mean, it might be like block sparse blah by symbolic size. So I mean, I'm making stuff up because I don't know, but I mean, the question of the types versus operands is exactly that. Or if you're taking an attribute based approach, do you know for certain that you never want to parameterize that?
No,
well, I guess
I think
kind of also, this also hints as these dependent types and this kind of, I guess, magic trailing operands that we could add to any op. Like if we had a trailing operand interface or whatever that we could add to any lineal job, then you could do whatever, exactly the same thing that IREE is doing with the whatever tied outputs, right? To pass the SSA values, and you could actually encode a transformation there because you would have what you need, and that would be the same thing as so instead of applying it, you could actually transport it, and that would be rich and general in the sense that I don't need to write 20 different attributes and be sure that all instances of the usage of these attributes in the compiler agree. I can just actually say apply this transformation, and then it will apply it at some point. Like basically you register that you're going to apply this transformation and make it unsurprising, I would say.
Yeah, and you could imagine, you know, maybe it's a little bit of a stretch and affine maps still scare me, but kind of like affine apply. You you have an attribute saying what you're doing, and then you can have symbolic values that you capture along with it. Here, effectively, we have the enums that we're using today are like aliases for some affine map. And the symbolic values are implicitly defined in the backends as they can query tile sizes and stuff like that. But we could make those explicit as well. It would just be the selection of what's near the front of the pipeline you choose to make symbolic. If it's based on the program or a user tuning value or something like that, that's one thing. If it's based on the hardware architecture, then that's something that kind of gets harder to query at that level.
I'll tell you all a management trick is that you watch other people's faces when someone is speaking and know what expression they have. That means that you just added 9 months of work to my plate.
What? It's fine maps. They're easy, right?
Actually, I mean, it's interesting, Afan, because I think one of the earlier proposals from Lorenzo was for the pack operation to use affine mapper to define the pack. I think that's what they started with in their development. But when they started moving it upstream, staging it in IREE and then moving it upstream, we kind of like affine maps is too heavyweight to describe that. Let's go with like something that is very simple to describe because that's what we need. But maybe affine maps are the final solution.
Oh, it would be affine maps with the generalization that being some mechanism to capture the symbolic values for them on that set encoding.
Don't really. Oh yeah.
Or at least knowing you can elaborate to that at some point.
You just need to know. So here, for example, the assumption is that your right-hand side needs the same kind of affine maps, but the value of what you use for the tile size is different, and that is architecture dependent. So the affine map itself might be okay across architecture. If you want to be that specific for an architecture, that is kind of outside of it.
Well, you might. We're out on a limb here on how general do you want this to be, but if you wanted it to be that, you would still have some of the placeholders are known to be runtime defined symbols. Some of them I can imagine in a fully generic setup are SSA captured in some way.
We can still have the implicit ones that are hard to model atomically at this level.
I don't know what level of generality you're after, but it seems like that's the axis.
And what's nice is this set encoding and unset encoding are just kind of the front end ops. Once it gets into pack and unpack in the back ends, it's kind of fully explicit. And so I think what's nice is if we decide to completely change how we reason about these things at the flow level, and as we're doing this, shouldn't really change the rest of the system. So I think there's room for iteration here. There's room for alternates.
Yeah. Yeah, I think that's what I said. The pack and unpack are like supported operations from the front end. So you could have a pack operation. And as that evolves, if that satisfies the generality, we could use that as the front end. This is just like one way to kind of low overhead way to do it without having to re-engineering the whole system when you wanted to change direction.
And we've got the meme 0 days since we've been independent types.
Because the other thing here that we'll eventually get to, people ask about heterogeneous compute and stuff like that. When we start crossing devices that might have different parameters for these things, that's where we need to, at a higher level, be able to reason about, we told it to pack into this form on this device, and then we're consuming it on this other device. We need to reconcile those, and how we do that will be interesting. It's done in lots of domains. You end up with non-optimal, but still somewhat optimal forms as intermediaries between devices and things like that. And those are the kind of things that would be much harder to do if we had already baked it out into a particular form ahead of time. We can't decide to move some work to a GPU and some work to a CPU, or a DSP versus the main general compute. We'll get there when we get there, but the idea, at least anyway, is that starting at this point gives us that flexibility to explore that space where if we were to hard code it, we would never be able to get there.
Yes, see, this discussion reminds me of Jeff's late night proposal from PLDI that he pinned up that upset everybody. So like it's always fun to depend in the section. But I see Kojo has had his hand up for a bit.
Yeah, thanks. I was fine with the discussion. Continuing, I just had a thought on the trying to connect this to what this looks like on the ground. So you mentioned Kudo's future work. Can you speak a little bit about what the pack and unpack ops would look like, say on the Kudo backend? Particularly as you emphasize, the key here is really how these are fused with their producers and consumers, or you're amortizing the cost that actually gets you to speed up?
I'm not sure I know what the question is, because it basically is. Let me go back to the backup. There's no much different here. This is yeah. The difference would be the values you use for the outer DIMS permutation and all the different things listed here. So at the level in the CUDA backend, what the specific values of those things are picked in the CUDA backend to say these are the values I want. Today we picked something that works for ARM. Actually, it's structured so that for ARM we picked this, and Benoit did some work to pick a different set for x86. But those shouldn't matter so much in terms of fusing with the producers, because you're never going to. All those are doing is changing what the inner tile size is. You're only going to be fusing along the outer dimensions. You don't want to go and fuse with the innermost tiles of these computations, because they map to something that is a unit of work on your hardware. So you're expecting them to happen in like sort of an atomic step, where you just perform those computations. And then the result of those computations, how they get used, is kind of what the fusion and all those things are. So it should not be very different. The kind of things that you would have to do to generate code on CPU would be similar to what you would have to do on the GPU, except you have another degree of parallelism that you need to account for.
Yeah, and concretely, like these ops, they're not magic. Like the outer DIMS, for example, might change the stride that you're using to walk the right-hand side if you're transposing, and then the inner DIMS might introduce or remove the need for a shuffle or permute operation. But that's kind of it at the end of the day. The expectation anyway is that is all this ends up being.
Manish, you had a question?
Yeah, so do you think for CUDA it will need newer encodings, or the current encodings can be used?
I think the current encoding can be used. We might have to just not use the output encoding if you really want to keep the fusion. But
if there are encodings, is just the algorithmic specific performance optimizations, or there to the encoding there is also some architecture stuff. There is some architecture specific stuff to encoding.
There is architecture specific stuff in the sense that for the particular operation, you want to know what the tile size is, and that may depend on, for say, matrix multiplier depends on the tensor core sizes. So the actual value of these might be different based on the architecture you're doing. But broadly, also these enums, you could interpret them how you want on. So you don't need a different set of encodings. It's a matter of how you interpret the encodings on different backends. Like a right-hand side of a matrix multiply has some layout. What that layout actually is completely up to the CUDA backend to decide. You don't need to add a new encoding for the right-hand side of a matrix multiply. It's the same encoding. It's just you interpret it differently on the CUDA side, and since all the dispatches interpret it the same way, it's consistent across the program.
Okay. So encoding has an enum, and based on the architecture, so if I define it like the encoding is defining a layout where layout is a mapping from a coordinate space to an index space, and then that mapping is some function, some math function, and based on the enum, you will apply a math function that is mapping the coordinate space to the index space, and now on using the same enum, you can apply a different function.
Yes.
Yep.
If I understand that correctly, that's right. That's exactly what we do on x86 and on ARM. And some preliminary work that I saw Gure was doing on CUDA side. It's just how you interpret it is different.
Thanks.
Yes, Kojo.
I don't know if this is related, but one thing I've noticed looking at various models, usually preceding a map mole will usually have some sum over transpose. I'm guessing to get one of the right-hand side in a format. So there would be conditions for the matmul. And this is pretty common. I'm curious if this would address that, like, because we've talked about, efforts to fuse that into the matmul on the CUDA side. So we don't have separate dispatches before every matmul. That's essentially rearranging your right-hand side.
Right. So I think there are two things here. One, maybe that is a little bit of a premature optimization being done, where the transpose is being introduced by the front end, where it's making a decision on how this matmul has to be executed on the device. So there's a little bit of that leak happening. If you didn't have the transpose, you could basically what the packing of the right-hand side does is the transpose. It's transposing it so that you get contiguous access. So you could use that to fold it away, but that gets opinionated because you have to then know folding it is harder the way you're using the encoding, because you would have to fold it at the flow level, and that is abstract. So in theory, you don't have that information. To me, having the transpose, if there's a way you could avoid having that transpose coming in from the input, and instead just leave it as a matmul or some other operation and use the data padding, the packing and unpacking to get the layout you want, and that's a decision made in the back end, that layer's better. So there might be a couple of things going on.
I think you're going to run into the case that there will be transposes or not, and they're effectively noise in the program, and you want to fold them in, and then there's going to be an optimization pass somewhere that decides.
Yeah, but then the folding those transposes in means that you have some information about what the layout that you're using in the backend is going to be. Otherwise, I don't see how you could.
Well, you can always refold them.
Yeah.
Look at how XLA does this, for example. It can add it can fuse a transpose with just about any op because they are effectively noise in the program.
Yeah.
And you optimize that. So
Yeah.
Would this folding be done at, because like we've talked about this in terms of folding at the backend level with the knowledge on say CUDA that like we can do a matmul with an implicit transpose on the operands. I don't know what that looks like at the flow level though, because there's not really anything to represent that.
Yeah, and those kind of things get tricky because there's capabilities that you have, but then there's reasons why you would and would not use them. So it is never going to be efficient to not transpose the right-hand side, even if the hardware might let you do that by like providing automatic striding of memory loads, because you're going to be making a lot more memory transactions, and that's often a limited resource. But if you otherwise would have had to do a dedicated dispatch and a full read and write through memory in order to get it transposed, they can be better. But this becomes like a pretty complex cost modeling thing. So yeah, it gets very hairy at that point where you're talking about these kind of data layout changes. I don't think we're there yet. Likely all of this stuff will come from annotations done by, profile guided optimization and stuff to start before we get to the point where we're automatically doing that. Humans are really bad at this today, as well.
Cool.
You can look at a specific case that you have and walk through it and see what's happening. To see
Yeah,
what
I can show you at some point.
So I'll jump in here, I guess. You may be interested to take a quick look at the draft PR that I sent. The reason is, so considering we can do code gen wherever, so purely in the pre-processing type of thinking, that PR, what it does is it uses actually data tiling or pack and pack as a way to normalize any contraction. Meaning that whatever the flavor of matmul with or without transpose is, once they're folded, meaning that whatever order of IJK and transpositions of the operands you give it, it will normalize to always the same matmul on this thing and adapt the pack unpack accordingly. So that's, I guess, part of the generalization I was talking about, because like with one thing, you can handle all contractions, like all of them, 3D, 4D, 5D, whatever. And then same thing for convolutions. With one thing, we should be able to handle all convolutions. And that's something that is pretty powerful. So we can discuss it next time.
Do you want to just read out what you post on chat?
Muted.
You're muted.
Yeah, sorry. I was just saying the root cause why transposing right-hand side is so generally useful beyond any specific hardware consideration like cache and striding is down to math. Matrix multiplication is not commutative. A times B and B times A are totally unrelated in general. But A times transpose B is almost the same thing as B times transpose A. Namely, it's the transpose. A times transpose B is the transpose of B times transpose A. In what I wrote in the chat, I had B and A swapped. So that math fact that matrix times transpose of matrix is much closer to being commutative than just matrix times matrix is the root cause why it's so useful at so many levels downstream from that abstract math level to transpose RHS.
That's a good point. Maybe that's why we see so many times.
Sorry, I didn't hear.
No, maybe that's why the transposes are coming from in the models. Because
Yeah.
you want to get the A transpose.
Yeah.
Well, I
These
mean,
transposes-
they're really coming on because people have a matmul. They just know about matmul, right? So then you need to transpose B in order to get the commutative property or close to commutative property. But if you have an einsam op, you don't really care that it's a matmul or a whatever. Like the op semantics can change and give you the transpose for free.
It also gets interesting with gradients, you know. But anyway, so I think we're running a little bit out of time today. You know, thanks for the great presentation. So you know, if folks have more questions on this, please follow up, you know, online in the chat room or email, and we'll send out the recording soon. And please remember to fill in the form for topics of interest. Thanks very much, everybody.
Thank you.